All right, chapter 21, the last chapter on electrochemistry. And yay, let's do puns. I'm shocked that we're almost done. So, here's the deal. This is our last chapter. Like I said last week, we got to sprint a little bit for the next couple weeks. This should take today and Thursday. It's going to be a little disjointed because of the quiz on Wednesday. But we'll get through a bunch of it today. Let me say up front, I asked to do chapter 21 because electrochemistry for me is something I've struggled with. And I asked to do it so I can get better at it. It's not something that is conceptually easy to understand. I think it's hard to visualize why the things that I'm about to explain are happening on some level. So, no. So the question was, are we the guinea pigs? No, I've given this lecture. This is now the third time I've given this lecture. I tweak it a little bit every year based on what I think students' misunderstandings are and my own personal things that I think need to be improved. But this is not intuitive. A lot of things for you guys can be intuitive. A lot of you find stoichiometry to be intuitive, right? The math just makes sense for some of you, not all of you, but for some of you. This is something that I think is intuitive to a smaller percentage of the population. So we're going to start though with a review. Oxidation state is an elaborate bookkeeping technique that we use to keep track of who gains electrons and who loses electrons in a redox reaction. So let's review our rules. Pick a color. I heard red first. So how to find So apparently the word bookkeeping, I just learned, is the only word with 3 consecutive double letters in the English language. Very interesting. How to find oxidation state? Well, there's probably some random word somewhere, but okay. How to find oxidation state? Rule number 1. Elemental form. Your oxidation state is 0. So some of this should seem vaguely familiar. So, for example, O2, Fe, etc. Things in their natural form are 0. 2. Ion. If you have an ion, it's equal to the charge. So examples here. Na plus, Cl minus. Your oxidation number here is 1. Oxidation number here is -1. After that, now we're talking about organic compounds, molecules, things that are held together covalently. F is always -1. Why is F always -1? What's special about F? Most electronegative atom. It will always pull its electrons closer. It'll pull shared electrons closer to it as compared to anything else. 4 is tricky. Oxygen is -2, except OF2, H2O2. Yeah, except for those 2. Right, so any of these. In this case, F is always -1. So in this case, O is +2. The peroxide ion, O2 2-, the oxidation state of O is -1. Now, this almost never, you'll almost never see this. You know why they'll see this? For you to, that scared me a little bit. You'll see this so they can test you on your ability to know the exceptions, not the main parts, right? So that's why you'll see that. And then H is usually +1. The question was, does Rule 5 take precedence over Rule 4? No, but I'm trying to think of a case where it would matter. I don't think it. So like H can be -1 if you have a hydride, like sodium hydride. Right, so the question was H2O2. Well, O2 is 2 minus, right, in sum. So H is +1, each H is +1. Oh, you could, if you used Rule 5, you could determine Rule 4, yeah. Okay. So now we need to take this bookkeeping method and apply it to chemical reactions. So the whole reason that we care about redox reactions in this unit is for electrochemistry, to make electricity happen. So who's being oxidized and who is being reduced? Well, you guys can sneak ahead. Who's being oxidized and who's being reduced? Take a look at the next slide. Figure out the oxidation number for each species in that chemical reaction. The question was, for polyatomic ions, do you split them up? I wouldn't. I would keep it as one thing. You can. You're more than welcome to, but it takes a lot longer. If it stays the same on both sides, you leave it as is. All right, so let's see what we have. Copper, elemental form, 0. Silver is bonded to nitrate. Well, we have an ionic compound, so we look at the charges. So silver is +1. Now, the question came up before, nitrate, what should we do? You can break it apart. We don't need to because nitrate's the same on both sides. So we'll just leave the whole thing as -1, -1. We're really only concerned about things that are changing. If you were to break it up, okay, so you know the whole thing is equal to -1. You know O is equal to -2. So N plus 3 times -2 equals -1. So N equals +5. Right, that's if you were to break it up. Let's not do that, though. All right, Cu is +2. Ag is 0. Now we go back to our old friend. Leo the lion goes grrr. It does work. I think this is tremendous. Grrr. What? You can even remember me making like silly bear faces. Reduce is reduced charge. You can think about it that way too. I just like doing. I'll be honest. All these years later, I still go to myself. Okay, loses electrons, oxidized. So I look. Okay, which one lost electrons? I think it through my head because again, conceptually. This stuff is difficult for me. So I think back to my rules of Leo the lion goes grr. So, well, what changed? Copper went from 0 to +2. Okay, so what did it do? It lost electrons. So it was Leo'd. And silver went from +1 to 0, so it was reduced. Okay, let's try another one. Oh, sorry. I'm also very excited for opening day. It's one of my favorite days of the year. Of course, I won't be able to watch much of the game, but. So the question was, did Mr. Hamill and I plan the matching Red Sox shirts? No, but I knew he was going to do it. I think we've done it 3 years in a row, so. Not the same player. His is unnamed, and I wear my favorite player ever. Pedro was there. There will never be another. There will never be another Pedro Martinez. I've never taken a twin pick with Mr. Hamill. No. There was some cursing involved in the desire to have Mr. Hamill and I take a twin pick. Okay. So try the next one. All right, try the next one. Okay, so hydrogen in its elemental form, 0. Oxygen in its elemental form, 0. O minus 2 from rule of 4, H plus 1. So Ger is what? Oxygen. Leo is hydrogen. Now, an interesting thing that we can learn from this. Hydrogen was oxidized. Oxygen reacted with it, and hydrogen became oxidized. So, in this case, oxygen was what we call the oxidizing agent. So, the thing that is reduced is the oxidizing agent. And the thing that is oxidized is the reducing agent. So, it's just like a passive voice. So, in this case, hydrogen is passively, being oxidized, but it is acting to reduce. So it is the reducing agent. Oxygen passively being reduced, actively oxidizing. So they'll sometimes ask you questions on tests like, what is the oxidizing agent or what is the reducing agent? You just look, well, the oxidizing agent is the one that was reduced, and the reducing agent is the one that was oxidized. You just flip it. That's a good, really smart way of thinking about it. So you can just complete the sentence. Oxygen is being reduced by hydrogen. So then you know that hydrogen is the one acting on it. That is, unless you want to stay after 3:30. There's an X block question. Oh, so the question is it called an oxidizing agent because that's a role that oxygen frequently plays? I'm not 100% sure, but I would venture to guess yes, because a lot of these early reactions were studied with oxygen. Yeah, metals oxidized, so that's probably how it was derived. Can oxygen be oxidized? I would imagine so. Yeah, we'll get to it in a little bit, actually. We're going to, absolutely. Yeah, we'll talk about it absolutely in maybe not today, but at some later date. So I have, right, but there are multiple ways that we can do it. I'll show you one later on. Okay, so if this reaction is spontaneous, I'm telling you this reaction is spontaneous. What must be true? And not only is this important to think about, but for those of you taking the cumulative, I just want you to think about it for a minute. If this reaction is spontaneous, what must be true? Think about what you know makes things spontaneous. Ooh. All right. I'm going to go with newer voices. All right, just go ahead, Becca. Okay, so that is one thing that must be true. Delta G is less than 0, not delta 6. Delta 6 is. Something else must be true. Why do you say that? So, well, the change in entropy is much less. Right. So it doesn't have to be that less than 0, but I just wanted to emphasize, you know that because delta G is less than 0, and you know delta S is much less than 0, because you're going from 3 moles of gas to 2 moles of liquid. If that is the case, then delta H has to be less than 0 in order for this reaction to be thermodynamically favorable. Okay. I think we're going to do one more. A little more complicated. Who's being oxidized? Who is being reduced? Oh, some people have already done it. I like it. I'll just give other people a minute. While I take attendance. Okay, so you should have gotten these as your oxidation numbers. +2, -1, +1. Now, going back to how did we find MnO4? Well, we know that K is +1. So this is taking us back to like the beginning of the year. K is +1. MnO4 then has to be -1 because our charge is balanced. O, so we have Mn plus 4 times -2 equals -1. Mn is +7. So, what was oxidized? Iron. And what was reduced? Manganese. Now, here's where it gets a little tricky in terms of terminology. You will oftentimes see, you'll hear that your reducing agent is not Mn. Your reducing agent is MnO4 minus. What's that? Oh, sorry, oxidizing agent. Sorry, oxidizing agent. I forget. That's always reduced. So that's where you get into the semantics. MnO4 minus is, it's not Mn that is referred to as the oxidizing agent. It's MnO4 minus. It's saying the same thing. That permanganate ion is the one that is doing the oxidizing. And in fact, this is a wicked strong oxidizer. A lot of like the fun reactions that, if you had Miss Ossipenko, she showed you fun reactions. A lot of the fun reactions, I think even the one we did at the beginning of the year, involves this ion because it's a very strong oxidizer. Yeah, Liz. So the question is, why is the whole thing the oxidizing agent instead of just the Mn? I'm not sure. I just know that it's considered, it's written that way. You would never get both of them as a possible answer, right? It wouldn't be like a multiple choice where like, what is the oxidizing agent? Is it Mn, MnO4? O doesn't change. But it's this ion that is involved in So the question is, how would you know it's the ion as opposed to just Mn? I would think it would be, this is not a great answer. I feel like a terrible teacher standing here and telling you this. It should be obvious from the question, right? Because if it's a multiple choice question, you're not going to have both. And if it's an open response, we'll take either. Right. I'm not 100% sure why it's considered that way, to be honest. Okay. It just might be semantics. Now, we can imagine splitting the reactions up into two half reactions. And this is where electricity is going to come from. Two half reactions, one where something loses electrons and one where something gains electrons. So this reaction we're going to keep coming back to. Zinc is 0. Copper is plus 2. Sulfate, the whole thing, is minus 2. Zinc goes to plus 2. And copper goes to 0. So if we watched this happen, we would see a metal, like grayish, that's grayish metal, put into a blue solution. And then we would see a clear solution and a, God, I don't want to call it copper metal, copper-colored metal, because it's a, what were copper. You would just see copper, right? So you would have a reaction where you started with a metal in a blue solution, the solution would clear up, and you'd be left with copper metal behind. When we used to classify reactions, we would call this a single replacement reaction, right? We're going away from classic, just classifying. Oh, that was a terrible two words to put together. General classifying and moving to like deeper understanding. So here's how we figured out. Start with the net ionic equation. Now, because it's on 2 pages, and I know some of us might not remember net ionic equations perfectly, I'm going to help you out. Solid plus, now we split up anything that's aqueous. And we get all right. So for that net ionic equation, what is the same on both sides? What did not change? SO42 minus. And what do we call that? Spectator ion. So my whole net ionic equation is just this. So from here, we take this and we split it up into 2 different reactions. And eventually we actually are going to physically separate these 2 reactions and make them happen. But for now, let's just see what that looks like. So what is being oxidized? What is, let's see, Leo, so it's losing electrons. What is losing electrons? Zinc. So the oxidation half reaction is just zinc. Solid. Something is not right. This is not a balanced chemical equation. What are we missing? Electrons. And we don't put phases of matter for electrons. The question is if you had to put a phase of matter to electrons. Right, I have no idea what you would even put. Right. So they're not, I don't even know if, not even plasmas. Right, so you would just put like an E. Like they're just electrons. They're just 2 electrons. Okay, so then this one, for the reduction, well, we know copper is reduced. In this case, though, it's adding 2 electrons. So we get this as our reduction half reaction. Yes, and if you add the oxidation reduction together, you get the net ionic equation. Whoa, mind-blowing. Now, one thing that we're not going to do that I tried, so the first year I taught AP chemistry was at my old school, and I tried to teach them how to balance complicated redox reactions. It's actually not that bad, and if I had more time, I could teach it to you guys. But it's much more complicated than classical balancing of chemical equations. You'll see these like like this one on the next slide, but much more complicated than even that. It's not like just counting the atoms on both sides and making sure they balance. There's a lot more that goes into it that thankfully we don't have to do. All right, so this is a new slide, and I had no idea where to put it. So one of the things that you guys need to learn about is redox titrations, which thankfully you guys are experts at titrations because you all have done them now for 2 labs, right? Experts? Yes. Right. Okay. So we do redox titrations for the same reason that we do acid-base titrations, to figure out the concentration of an unknown, right? So here we have, let's pretend we have unknown, a sample with an unknown concentration, right? And we want to know this. And we're given the concentration of our potassium permanganate. So, unknown concentration, but known volume. I want you guys to we got some time, take a couple minutes, see if you can come up with the oxidation half reaction and the reduction half reaction from this nasty thing. That's a good question that I don't know the answer to, so it doesn't matter. Ugh. I should have thought this one through before I did a little bit. All right, so because I want to move on, this is what you should have gotten for the oxidation half reaction. Just iron 2 plus makes iron 3 plus, and it gives away an electron. For a reduction, you should have had MnO4 minus plus 3 electrons makes MnO2. Now, here's where I said it gets complicated. I guess I'll do this one quickly. If you guys just did this, we're fine. But if you were going to balance it totally, you would add 2 waters onto this side to balance the oxygens. Then you'd add 4 H pluses on this side to balance the hydrogens. Then you're good. And you're good. But you do not need to know how to do that. There are if you're interested in the book, it walks you through how to balance an entire redox reaction, and it has to do with these steps. But what you really care about is the ratio between MnO4 and Fe. So, I have 3 electrons being transferred here and 1 here. So I need 3 times as much Fe as MnO4. Okay. So you could also get that from your mole ratio here. So this is being reduced, gaining electrons and becoming. That's what being reduced is. So that's the whole point. Like, this doesn't balance perfectly, and I showed you like how you would balance it perfectly. That's why you have to do all this other stuff. Okay. Otherwise, you're not accounting for some of the stuff that goes on. Right. All right. So there's a problem set problem when we finally print out the problem set. That you're going to go online, you're going to do a redox titration online. It's a lot less frustrating than doing it in person because we know this is going to work. So we have, let's do our diagram. We have our, what is this thing called? You're at, I've seen it spelled with an I or without an I. Okay, generally, in here, generally, solution with known concentration. So in this case, what did I say we know the concentration of? So we know the concentration of MnO4 minus in our case. I did not give myself enough room down here. That is a flask. Here is our analyte. And Kirby just used the word titrant, which is the correct thing to go in here. And analyte with a known volume. And in our case, this is Fe2+. And just like you guys had indicators for your reactions that you did, the acid-base reactions, you put in something, the color changed. Well, a lot of transition metals undergo color change. So you can see when your reaction is completed because you have gone from, I forget what color, this is like an orange to a blue or something like, I forget what the exact colors are. But when you change the charge on transition metals, you may change the color of that solution. So you can actually see it. So, oops, that's going to be orange now, isn't it? Right. All right. So let's say, give me a volume for Fe2+. Let's do 0.05 liters. Concentration of MnO4 minus. I'm just going to make it more. 0.187 molar. And so you run the titration. You find that the change in volume for MnO4 is 12 milliliters. I should have done the math before. So what is your Fe2+ concentration? Try it. See if you can get it. Okay. So I see some people still working. I see some people finished. And I see some people struggling. So the first thing I want to do is find the number of moles of MnO4 minus that were used. And so I'm taking out my calculator, 0.187 times 12, 0.187 times 12, divided by 1,000, and I get 2.24 times 10 to the minus 3 moles. I'm going to bring that down here. That's long. Now, I need a mole ratio, and this is where people often get lost. Yeah, 1 mole of MnO4 minus to 3 moles of Fe2 plus. So that is 6.72 times 10 to the minus 3 moles Fe2 plus. How do I go from moles to molarity? Divide by volume. So 6.72 times 10 to the minus 3 moles over 0.05 liters. And what do we get? 0.135. Yeah. So the question was, and it's a very good one, isn't it easier to just do M1 V1 equals M2 V2? And if you look at my notes, that's what I wrote down when I was the only problem with M1 V1 equals M2 V2 is you have a mole ratio. So if you do M1 V1 equals M2 V2, just be careful to do your mole ratio at the end. Otherwise, you'll get it wrong. Yeah, but that's certainly, obviously, I thought it was good, and then I just decided to call an audible right now. Yeah, so the online one is actually, I don't know, it's fast. It's so much faster than doing it in the lab in the back. All right, we ready to move on? All right, the next two things you should know. Now we're getting to that table I gave you. The standard reduction potential for a half reaction. Remember, we can split oxidation reduction reactions up into half reactions. The standard reduction potential for that half reaction is a measurement of how much potential energy changes when that reaction happens. So, do we want to gain potential energy? Does the universe want to gain potential or lose potential? Lose. We want to go to lower potential energy, right? So, using this table, we can calculate the potential energy difference for an entire reaction. This potential energy difference is another way to tell us if a reaction is, we're not supposed to be using this word, thermodynamically favorable. The question is, wouldn't it be like electrically favorable? Yeah, but it's all thermodynamics. Okay. Now, standard reduction potential. Oh yeah, go ahead. We will get the question. The statement was, if that is true, then delta G will be less than 0. We will get there. We certainly will get there. Okay, so let's start with breaking this down. What does it mean for something to be reduced? Gaining electrons. It's gaining electrons. So what you get, that list that you got, is the potential of that half reaction at standard conditions. And I know there is a lot of, we'll get to the comparison in a second. I know there's a lot of hand-wringing about what does it mean for something to be at standard conditions. This is when we start to care, really. Because what's a symbol that I can put that means important? Exclamation point. It looks like I'm cursing on the board. Okay. All right. That's not a euro. All right. Okay, anyway, this is important. Yes, Jonah. Oh, you predicted, and Kavish was just about to had mentioned earlier, you predicted like what I'm going to write in 2 lines. Yeah. Mind reader. All right. Actually, not even 2 lines. So I'm going to put, and I'm also going to put this in a box. 1 molar concentration. I know that it got like messy. It got hard to read actually. I like overdid it. So 1 molar concentrations. All of these half reactions are at 1 molar concentration. It's going to change when you change your molarity. Now, because Jonah is a mind reader, all values are referenced to this. So that's exactly right. You're comparing how much more or how much less the potential is than, and I'm going to put this in a different color, than this half reaction. And the units for E naught, or for E, are volts. And something we're going to need later on when we do some stoichiometry. Does anybody know how volts are broken down? Not you. Joules per. You're almost there. How do we measure charge? Volts are joules per coulomb. I love it because we're actually doing this in freshman physics now. We're getting into electricity, and so I'm like, oh, it overlaps. And I have a much better understanding of freshman electrostatics and electricity, having taught this class for a while. Oh, it is the push. It's how many joules, how much energy the electrons have per coulomb of electrons. So it's really good. Okay. So everything is in reference to this. On your sheet, you should also see that this reaction is listed on your sheet as the 0 point. Okay. So finding the overall potential for reaction. Well, step 1, net ionic equation, which we've already done. Not copper sulfide. All right. So we already did this net ionic equation, so I don't need to derive it for you again. 2, do the half reactions. So we have Zn makes Zn2 plus 2e minus aq. Whoever's making that noise, please stop. Okay. Here are 2 half reactions. It's okay. But, all right. Here are 2 half reactions. Now, look on your sheet. Can you find both of these half reactions as written? You should not be able to. Not as written. What does that table give you? Backwards. The table gives you backwards. All right. So, now, you have to think to yourself, this is my reduction, and this is my oxidation. Now, this looks an awful lot like the flipped version of the one on your table, right? So you can find the E naught for this reaction, and what do we have for the E naught for this reaction? 0.34 volts. What is the E naught for this value? Well, if it's positive in one direction, it's negative in the other. So positive point. So for oxidation half reaction, flip the sign. So all you're doing here is you're taking what was written and you're flipping it to get taking what was written on the paper that you have, it's flipped, so you just switch the sign. So your total E naught is 1.10 volts. So the question is, what does that mean? Well, it means something that we'll delve into on Thursday. Really, if you set this reaction up as a battery. No. This is both thermodynamically favorable, which we'll get to. If basically what this is telling you is if you had these two reactions happening and put a wire between them, the voltage you would get on that wire is 1.1 volts. This is how batteries work. Right? You take two materials based on their different reduction potentials, you can get electrons to flow. Okay. Which is pretty cool. We will get there. The question was, how do standard reduction potentials tell you if it's spontaneous or not? We will get there in approximately 2 slides. Yeah. So look at your reduction. The question was about lithium-ion batteries. Look at your reduction potentials. Where do you see lithium? All the way at the bottom. So, I don't.